The application will now be discussed, very important application of the operation 1 by FD to find particular integrals of differential equations. That means we want to find particular solutions which cannot be obtained from the general solution, which is also called the complementary function. Now let us do a little bit of recap. Equation that we are going to discuss is of the form d2 plus a1 constant d to the power of 1, that is d, plus a2 another constant is applied on y gives the function capital Xx. This is the differential equation. We will explode this symbolic operator form of the equation to see it real. This is d2y dx2 plus a1 dy dx plus a2y is equal to capital X, which is a function of small x. So here it is evident that y is the dependent variable and we are looking for y in terms of x as a solution. Again, a little bit of recap. Our first task is to see how one can find the complementary function that is called y sub c. This equation has two parts to the solution. First part is called the complementary function, which can be denoted as y sub c, and the second part is called the particular solution, and that is denoted by y sub p. Now, this complementary function has as many independent arbitrary constants as the order of the equation. So, for any kind of equation like this, there is bound to be a complementary function that has two independent arbitrary constants. But the particular integral is the one which is the focus of our discussion here, and that will be without any arbitrary constants. It may have constants which have a fixed value, but certainly it is bereft of any arbitrary constant of integration. So that is the focus of our discussion, how to find the value of 1 by fd applied to this function that we will see. Let us draw out this part and then we will see how it works. Now, for the complementary function, we set the right hand side equal to 0 and get an auxiliary equation which is m squared plus a1m plus a2 is equal to 0. And find the values of a1 and a2 that satisfy this. We all know, we've seen earlier that there are three cases: m1 not equal to m2 and they belong to the set of real numbers. Second case is m1 is equal to m2 is equal to one common value and m belongs to the set of real numbers. Third case is m1 and m2 are complex, and from the theory of equations they have to be complex conjugates of each other. So the roots are like alpha plus minus I beta. In other words, one root is alpha plus I beta and the other root is alpha minus I beta. The roots are complex conjugates of each other. We will very briefly, quickly write down the y complementary in each case. In this particular first case, the complementary function is C1 e to the power of m1x plus C2 e to the power of m2x. This is this case. The second one, it is C1 plus C2x e to the power of mx. And in the third case, where the roots are complex conjugates, this is the real part, beta is the imaginary part. The solution is e to the power of alpha x into C1 cos beta x plus C2 sin beta x. So these are the three solutions, but again our real focus is what we want to do is to find the inverse operator applying on x, and that gives us the particular integral. So we write that straight away. What we have done a little while ago is just to recap, and that's good. We remind ourselves many times of the complementary function and particular integral. Now, pi is, if I call this fd, y is equal to, in fact, yp, 1 by fd operating on x. This we have discussed earlier, but the point is, given a particular expression for fd and different functions of x, different forms actually, exponential, maybe exponential multiplied by polynomials, polynomials only, and so on, or trigonometric functions, then how is it possible to apply 1 by fd operating on x given fd? So we will take some cases and see how to apply or how to get to the particular integral 1 by fd applied on x. First case we are going to take is case 1, we'll call it, is when our function capital X of x is e to the power of ax. Then the rule is one by fd operating on x is equal to 1 by fd operating on here, it is e to the power of ax, that is 1 over fa e to the power of ax, provided fa is not 0. That's understood. Now the question is, what happens if fa indeed becomes equal to 0? So we'll continue writing if this is not equal to 0, or it is equal to x e to the power of ax f dash a. We'll put the x a little outside, like this. x e to the power of x divided by f dash t, again provided fa f dash t is not equal to 0. In other words, this does not vanish. Question is, what happens if this does not vanish? So, or x to the power of 2 e to the power of ax divided by f double dash a, again provided f double dash a is not equal to 0. Sorry, no, is not equal to 0. So this continues. In fact, you can go up to x to the power of n e to the power of ax f n primes a, provided that n prime of f d or fx does not vanish for a. We'll take a simple example. Let's see. We've taken the function e to the power of 4x and e to the power of 2x purposely to reveal one property. First of all, let us start with this one. Capital X is indeed of the form of e to the power of ax, with ax having a value of 4. So, this leads immediately to 1 over 4 squared minus 3 into 4 plus 2 operating on, now it's not operator, it is a expression. So this is nothing but e to the power of 4x divided by 16 minus 12, 18 minus 12 is 6. E to the power of 4x was the right hand side of the equation. In other words, my expression here is b squared minus 3d plus 2y is, the equation is e to the power of 4x. So the particular solution is e to the power of 4x over 6. In other words, number one, this does not contain any independent arbitrary constant. It contains a constant 6 which is allowed. Number two, we will satisfy ourselves that this indeed, e to the power of 4x over 6 is indeed a solution of this particular equation. B square minus 3d plus 2y is equal to e to the power of 4. Then we feel things. We get to know that yes, indeed, what we say about complementary functions and particular integrals, they do really, each in its own right, satisfy the original equation. It's a very important property. The complementary function satisfies the equation, the particular integral also satisfies the equation. So let us see, question is, does e to the power of 4x over 6 satisfy the equation To answer this question, we will have to evaluate this expression with y as e to the power of 4x over 6. So, if we operate this function on this and indeed get e to the power of 4x, then we can say that e to the power of 4x over 6 is certainly a solution of the original equation. We'll do that. d2 minus 3d plus 2 operating on e to the power of 4x divided by 6 is nothing but, first term is d2 operating on e to the power of 4x by 6. So 1 by 6 d2 operating on e to the power of 4x minus 3 by 6, that means minus half, d operating on e to the power of 4x, and 2 by 6 is 1 by 3rd e to the power of 4x. Now we'll do this one by one. There is a minus term here. Okay. 1/6 is outside. d2 on e to the power of 4x will be 16 e to the power of 4x. So this is, first term is 8 by 3 e to the power of 4x minus d of e to the power of 4x is 4 e to the power of 4x. That divided by 2 is minus 2 e to the power of 4x plus 1/3 e to the power of 4x. If this is 8 by 3, this is 1 by 3, that's 9 by 3, 3 times e to the power of 4x minus 2 times e to the power of 4x. The net result is e to the power of 4x. So we can certainly come to the conclusion that yes, indeed, my function e to the power of 4x over 6, and mind you, it is e to the power of 4x over 6 alone. It's a fixed constant, it's not arbitrary. It's a fixed constant. If you make this 5 or 4 or 2 or any other, it will just not satisfy the original equation. So that is the beauty of a particular solution. The next one we chose was to find 1 over same FD applied on e to the power of 2x. So our equation will now change for the second case, e to the power of